thermal comfort. In this project, I'm focusing on the last application. So the governing equation for PCM in building is mainly energy, because mass and momentum is conserved and we don't have any problem with that. And using that equation, we can discretize it and solve it to get the temperature. But the main issue when phase change starts, this is fraction that is already changed the phase. Let's say here it's solid to liquid, and we cannot use this as uniform integral, which makes life easier to solve this. To do one equation here, we have to change this Cp as effective phase change, and having said that, there is no change in density or change in thermal conductivity with time. We can approximately take them 0 and solve this equation. And this is effective Cp that would be substituted to give one integral here. And we end up with this equation, and discretizing this, we can get the temperature versus time and then investigate that. So having said that, let's see how PCM work with respect to sensible material like water. When we heat up the PCM, it just passes through this path, which is fixed temperature, and heat absorbed, and then in the reverse release. And the important thing PCM in building science is this temperature should be within set point. Otherwise, PCM really doesn't have any help based on latent heat. It just works like sensible. So, saying that, the PCM that I'm using to simulate is this PCM, which was developed in Halifax University, I guess. And this is how it works in, let's say, ambient temperature and solar radiation in the red during the day, noon, or afternoon. We have maximum radiation, and temperature, of course, is high. But at night, temperature goes down, but there is no helpful radiation. So using PCM, we can shift this using that latent heat and a little bit reduce that fluctuation inside. So we have outdoor fluctuation, but not that much indoor, thanks to PCM. So doing that, this is the wall layer for SUI building that I showed already, 3-story building with mezzanine. And this is floor or ceiling for the next zone, up and down. And this shows how much PCM used in different zones. We have garage, we have first floor, second floor, third floor, and mezzanine. So this is typical simulation which is used for PCM. During conventional simulation studio, you can see PCM for different zones is added. This is chassis built, which with this I can define the layers on the wall and floor and all information given to the simulator. And then I can get temperature of different zones. Of course, it's not that clear, but typically this is the bunch of information that I can get. So I can filter it and give you the result. During simulation, I was using shading schedule because it just saves energy a little bit. And as you see, during winter there is no shading. In shoulder season it's half open, and in summer it's closed, maximum shading. Again, no shading. And right now I have to input weather information. That's the reason I added frontal. So right now I have to add weather information to get the result. So to analyze the temperature inside, I'm not taking temperature of the air inside, but I'm using operating temperature, which is more closely to the temperature that we are feeling. So temperature of the surface and temperature of the air with A, which is almost half here, can give you operating temperature. And to define the effect of PCM, I have a few index. So one of them is delta T, which is the absolute value of temperature of the indoor when PCM is there, minus temperature of no PCM at the same time. And another index that I'm defining is average delta T during the year. In whole year is 8,760 hours. So this delta T with bar gives me average temperature difference. And I'm defining average hourly temperature fluctuation index, which is